Hello there and welcome to the Sleepy Science Channel, a quiet little corner of the universe where curiosity drifts softly through the dark like mist over still water. And tonight we are traveling into a part of nature that most of us never truly see, a world that comes alive only after we close our eyes, a world sculpted by moonlight, painted by starlight, wrapped in shadow, and carried on the soft hush of nighttime air. A realm shaped by the rhythms of creatures that thrive when the rest of the world slows down, a hidden universe filled with strange forms, delicate adaptations, ancient instincts, and powerful senses refined specifically for the darkness. Because the night is not simply the absence of day but an entire ecosystem that operates with its own rules, its own signals, and its own secrets that unfold gently when daylight fades away. And within this darkened world nothing behaves quite as it does under the sun, for the animals of the night do not simply tolerate darkness. They master it, shape it, and interpret it in ways that feel almost magical to us, using whispers of sound, faint glimmers of light, subtle changes in temperature, tiny shifts in air pressure, and patterns written across the sky, transforming the dark into a landscape of information, responding to cues that we rarely notice, moving with precision through spaces that appear opaque to human eyes. And so, if you enjoy these quiet journeys into places that hum softly beneath the surface of everyday life, I invite you to like, subscribe, or share your thoughts below because every little interaction helps another sleepy soul find their way here. But for now, the only thing you need to do is relax, breathe gently, allow the rhythm of your thoughts to soften, and let these nighttime wonders drift through your mind like a lullaby as we begin exploring the incredible ways nocturnal animals interpret, navigate, and survive in their shadowed world, starting with the astonishing behavior of creatures that navigate using the Milky Way itself. Because some nocturnal animals, small, soft, and unassuming, have evolved the extraordinary ability to use the hazy band of our galaxy as a stable reference point during nighttime travel across open terrain, solving a serious problem faced by species that must move swiftly through environments where ground shapes disappear, where open fields become featureless voids, where the horizon blends seamlessly with the dark sky, and where even the slightest deviation in direction can lead to circular paths or confusion. To overcome this, these animals briefly glance upward, read the broad structure of the Milky Way, compare its orientation to their own heading, and reset their path with remarkable accuracy, relying not on individual stars, which are too faint and too numerous, but on the diffuse, glowing band stretching across the heavens. Using its position like a cosmic compass, an ancient signal written far beyond Earth but vital to tiny lives navigating grassy plains or sandy deserts. And this behavior is not a vague attraction to light but a deliberate, practiced navigational technique that persists even when the moon is absent and darkness is nearly complete, showing how deeply evolution can connect survival on the ground with patterns traced across the universe. And from here the night deepens further as we step into the world of bats, who use sound not simply as echoes bouncing from surfaces but as a dynamic, continuous map of space, producing calls of varying pitch, timing, and intensity, each shaping a distinct piece of information, each crafting a new measurement of the world around them. And when these sounds return, even with the faintest distortions, their extraordinary brains decode distance, movement, softness, texture, and direction faster than a blink, building a living, shifting, three-dimensional model of the environment with every beat of their wings, allowing them to snatch tiny insects that twist unpredictably through the air, avoid branches hidden in the dark canopy, slip through tangled roots and cavern openings, and fly through narrow spaces where even daylight would offer little help. And still, deeper into the night we drift, toward owls, whose flight is so quiet that it borders on supernatural, engineered by evolution through specialized feather structures, serrated wing edges that shred incoming air before it turns turbulent, fine fringes that break up sound into harmless wisps, and velvety surfaces that dampen vibration, all working together to allow these birds to glide like ghosts through forests, fields, and snow-covered landscapes without alerting prey. And this silence not only helps them hunt unsuspecting creatures but also enables their own hearing to remain unobstructed, allowing them to detect even the faint rustle of a mouse beneath leaves or snow. And then, beneath the sands of moonlit deserts, we find rodents whose survival depends on detecting vibrations rather than sound, because sand muffles footsteps and absorbs noise, making predators nearly silent as they stalk across dunes. Yet these rodents have evolved in large auditory structures tuned to low-frequency waves that travel through the ground, allowing them to sense tiny shifts in weight, slides of paws, or distant steps long before danger arrives, reading these vibrations like coded messages written in earth, and responding instantly by sprinting, leaping, or diving into burrows, using the cooler nighttime temperatures that change how sand transmits energy to their advantage, creating an entire sensory world beneath the surface of human awareness. While in other places, like humid forests where moonbeams scatter between branches, certain nocturnal spiders rely on air currents instead of sight. Their legs covered with sensory hairs so delicate they move in response to the slightest disturbance, detecting not just the presence of moving objects but the patterns of airflow created by wing beats, footsteps, or shifting leaves, enabling them to judge direction, distance, and even species identity, allowing them to strike precisely at prey hidden in darkness or retreat from threats that attempt stealth attacks, turning the night breeze itself into a living canvas of information, and deeper still into the forest we move. Discovering small nocturnal animals whose bodies produce faint glows, not bright enough to illuminate surroundings, but soft enough to be seen by others of their kind, patterns traced along fur, around eyes, or across skin, each glowing marking carrying signals used for mating, avoiding conflict, maintaining group cohesion, and navigating dense habitats where sound might draw unwanted attention, creating an intimate, private language of light that only becomes visible when daylight disappears, allowing families, partners, and group members to recognize each other without revealing themselves to predators. Demonstrating how nighttime communication often becomes a matter of balance between expression and concealment. And beneath dark waters, where even moonlight cannot penetrate, certain nocturnal fish navigate and hunt using faint electromagnetic fields generated by the muscle activity of nearby animals, sensing distortions in this field with specialized receptors scattered across their bodies, enabling them to locate prey hidden in vegetation or murky water, track movements regardless of visibility, and remain undetected because their method is passive, requiring no signal emission of their own, a quiet, patient form of perception perfectly suited for nighttime hunting when other senses falter. And in humid jungles, we encounter frogs that alter their skin chemistry after sunset, producing compounds that change how light reflects from their bodies and how their scent disperses, helping them evade predators that hunt using vision or smell, a nightly transformation that resets the rules of camouflage depending on environmental conditions, humidity, moon phase, or the presence of competitors, showing that even the surface of an animal can become a shifting tool adapted to darkness. And if we continue wandering through this midnight world, we find countless other examples: moths that detect the slightest trace of infrared radiation, snakes that track heat patterns left by passing prey, deep-sea creatures whose bodies shimmer in silent forests of bioluminescent light, and mammals whose whiskers interpret air movement like extensions of their own minds, each adaptation a reminder that the night is not a void but a vibrant, living world, a place where evolution has driven senses to extraordinary extremes, where survival depends on listening to silence, reading starlight, interpreting patterns we cannot see, and understanding signals written into ground, water, air, and sky. And as you let all these images drift softly through your thoughts, these glowing forests, whispering sands, silent wings, shimmering waters, and cosmic compasses, feel your mind becoming quieter, slower, more peaceful, as if the night itself is wrapping gently around you, inviting you to rest, inviting you to breathe in the softness of the dark and exhale the weight of the day. Because the journey through nocturnal life is not only about learning, it is about letting the calm and quiet rhythms of nighttime creatures soothe your senses, reassure your mind, and guide you gently towards sleep, where the world softens, where shadows become comforting, and where the quiet wisdom of the night carries you peacefully into dreams. Nocturnal life unfolds in ways that most of us never witness, a world shaped by moonlight, starlight, shadow, and the deep quiet that settles across landscapes after sunset, revealing creatures whose survival depends on mastering the darkness rather than avoiding it. And as we explore this hidden realm, we see how animals use senses far beyond our own to navigate, hunt, communicate, and thrive when light is scarce. Beginning with frogs whose nightly transformation illustrates the astonishing biochemical adaptations that support survival after the sun goes down. Each evening, these frogs undergo subtle but highly effective changes in their skin chemistry, producing compounds that adjust the way they reflect light and emit scent, helping them blend seamlessly into nighttime surroundings where visibility is limited and predators rely on faint cues to locate prey. And these compounds scatter light to soften outlines while simultaneously reducing chemical traces that predators might track, allowing the frogs to move safely through environments where hiding places are few, a strategy made even more effective because the transformation completes precisely when temperature, humidity, and predator behavior shift, meaning the frogs do not depend on a single static form of camouflage but instead update their defenses in real time to match the conditions of the night, demonstrating how even small biochemical adjustments can create significant advantages in ecosystems defined by darkness. Much like these frogs, night-flying birds specialize in navigating environments where traditional visual cues fade, using an incredible internal compass that allows them to sense Earth's magnetic field through receptors that respond to directional, intensity, and inclination changes, enabling them to orient accurately even when the sky is obscured by clouds, the moon is hidden, and stars offer no reference points. And this magnetic guidance not only directs their migration across vast distances but also helps them travel between feeding areas, maintain steady trajectories, and compensate for sudden shifts in wind or weather, proving crucial for species that cannot afford navigational errors when food sources and safe rest sites are widely spaced. Meanwhile, some nocturnal mammals possess ultraviolet markings that appear only under moonlight, providing a quiet and private form of communication invisible during the day because sunlight overwhelms UV wavelengths, but at night, these markings glow faintly, revealing patterns readable only to members of the same species, conveying information about territory, reproductive status, or group identity without attracting predators, and because the patterns appear on specific parts of the body visible only at close range, they promote accurate, controlled interactions suited to dense forests or scrublands where visibility is restricted and sound can carry too far, creating a selective, secretive communication channel perfectly adapted to nocturnal life. Geckos, too, display night-adapted abilities that exceed human limitations, seeing colors in starlight through extraordinary photoreceptors that remain functional even when illumination drops to levels where human eyes see only darkness, enabling these reptiles to distinguish subtle environmental differences, identify insects trying to remain still, choose suitable climbing surfaces, and navigate intricate terrain with remarkable accuracy, and their eyes contain specialized structures that prevent blur, maintain clarity, and create stable images despite the extremely low number of photons available, giving them the ability to detect color cues from members of their own species as well, which are crucial in territorial and mating interactions. Bats, on the other hand, prepare for flight through physiological adjustments that begin long before they leave their roosts, warming their flight muscles in darkness because these specialized tissues require high temperatures to generate the rapid contractions necessary for powered flight, especially when emerging from cool caves, tree hollows, or sheltered structures where temperatures drop overnight, and through controlled metabolic processes, bats generate heat in the muscles that power their wings, ensuring they can take off at full capacity to chase early night insects that become active just after sunset. Because without this critical warm-up, they would lack the explosive acceleration needed to avoid obstacles, escape predators, or capture prey in fast-moving aerial hunts, and this preparation also stabilizes their movement during the first seconds of flight when air currents around cave entrances or forest edges may be unpredictable. Many owls enhance their night hunting abilities with facial discs, specialized feathered structures shaped like shallow satellite dishes that collect, funnel, and focus sound into their ears with extraordinary precision, enabling them to detect the faintest noises in grass, snow, or leaf litter, and their ability to adjust the angle and tension of these discs helps them filter out background noise while emphasizing specific frequencies, combining with asymmetrically positioned ears that compare sound arrival times from different heights to determine the exact vertical and horizontal position of hidden prey. And these adaptations allow owls to strike with near-perfect accuracy even when visual information is absent, relying instead on acoustic landscapes more detailed than anything humans can consciously perceive. Some rodents, living in environments where predators stalk silently under cover of night, communicate by drumming their hind legs against the ground, sending vibrations through soil and rock that travel farther and more reliably than airborne sound, especially in open habitats where wind disperses noise, and each species produces distinctive rhythms that signal general alerts, urgent threats, or territorial boundaries, enabling individuals to coordinate behavior, avoid unwanted encounters, and maintain safe spacing during nighttime foraging without relying on vocalizations that might attract predators. Meanwhile, many nocturnal insects exchange information using faint vibrations transmitted through leaves, stems, or soil rather than through sound, creating secretive communication systems that thrive in still nighttime air. With pulses that indicate reproductive readiness, food availability, or territory, and these insects possess highly sensitive organs capable of detecting slight mechanical shifts, interpreting complex sequences of vibrations that would be extremely difficult to transmit through speech-like calls, and because their habitats, from tall grasses to forest undergrowth, efficiently transmit vibrations, this mode of communication remains clear even in complete darkness, supporting intricate social and reproductive behaviors throughout the night. Together, all of these adaptations, from biochemical shifts to magnetic sensing, ultraviolet communication, color vision in starlight, muscle warming, acoustic precision, ground-borne alerts, and vibrational messaging, reveal a world where the absence of light does not limit life but instead inspires a breathtaking array of evolutionary solutions, proving that the night is not empty or silent but rich, layered, and alive with information constantly shared, detected, interpreted, and used by creatures exquisitely tuned to darkness, forming a vast and intricate network of survival strategies that unfold each evening when the sun sets and the hidden universe of nocturnal animals begins its quiet, wondrous activity. Certain beetles produce brief glows to attract mates during the darkest hours, and these glows, though tiny and fleeting, represent some of the most intricate communication strategies found in the natural world. The light they emit is created through a chemical reaction within specialized organs, a reaction that converts stored energy into visible flashes of bioluminescence. These flashes are short, controlled, and follow patterns unique to each species, functioning as a kind of visual language that allows individuals to identify suitable partners without confusion or wasted energy. Timing is everything, because the glow must be bright enough to be seen from a distance yet short enough to avoid drawing the attention of predators that prowl the darkness in search of anything that moves or shines. Nocturnal beetles perfect this balance by activating their bioluminescent reaction only at specific moments, typically when another beetle of the same species is most likely to detect it. Environmental conditions such as humidity, cloud cover, fog, and moonlight can influence how light travels through the air, so some beetles adjust the brightness, spacing, and duration of their flashes to match the night's changing atmosphere. These signals also help reduce failed mating attempts by preventing encounters between species whose patterns do not match. In dense forest habitats, where leaves and branches create a maze of shadows that limit the range of sound and scent, this light-based communication gives nocturnal beetles a major advantage. Through these delicate glows, they maintain a silent conversation across the dark, demonstrating precision, efficiency, and evolutionary brilliance. Meanwhile, several rainforest mammals rely on scent trails that disappear by sunrise. These animals, active primarily at night, use scent markers to navigate dense undergrowth where visibility is low and dangers lurk behind every trunk and vine. The chemicals they deposit degrade quickly when exposed to heat and daylight, ensuring that the information remains relevant only during the short window of nighttime activity. This temporary system prevents predators from following the same trails hours later when conditions have changed and the mammals have moved on. By laying these trails, the animals create routes that guide group members to feeding sites, safe shelter, and water sources while avoiding areas recently visited by predators. Because the scent fades rapidly, the animals must refresh their trails each night, a behavior that encourages flexibility and adaptation as they alter pathways in response to new obstacles, new food, or shifting environmental conditions. This reduces the likelihood of overusing the same routes, an important advantage in ecosystems where repeated patterns can attract unwanted attention. The markers also help individuals avoid danger by signaling zones visited by predators shortly before. The system demonstrates how nocturnal species build temporary, responsive communication networks that fit perfectly into the rhythms of night. Certain nocturnal birds rely on nighttime songs to mark territory, using sound instead of sight to convey messages that would be impossible during the day. At night, ambient noise decreases significantly, wind settles, insects quiet, and many diurnal animals sleep. In this acoustic stillness, a bird's song travels farther and remains clearer than it would in the daytime. This allows birds to establish territory boundaries without direct confrontation, reducing the risk of injury and conserving energy. Because visibility in darkness is limited, physical displays such as wing fluttering or body posturing are ineffective, so vocal signals become the primary tools for asserting dominance or attracting a mate. These nighttime calls differ from daytime birdsong in tone, structure, and repetition. They tend to favor clarity, simplicity, and recognition over complexity or ornamentation. Their timing is strategic. Many birds sing at hours when predators are least active, reducing the risk of revealing their position. The songs convey both warnings to rivals and confidence to potential mates, demonstrating how the challenges of darkness shape communication into a finely tuned art. Some frogs undergo nighttime transformations in their skin patterns that help them blend into the constantly shifting shadows of dusk and darkness. As the sun sets, gradual changes in pigmentation occur, triggered by diminishing light levels and the presence of moonlight filtering through leaves. These patterns match the irregular shapes cast by branches, vines, and uneven forest floors. Unlike dramatic color changes seen in some species, this transformation involves subtle pigment adjustments that alter how the skin reflects and absorbs available light, creating a soft camouflage that disrupts the frog's outline. Many nighttime predators rely on detecting shapes rather than colors, so blurring the edges of the body makes the frog far harder to identify. The camouflage begins to fade as dawn approaches, allowing the frog's daytime colors to take over when the visual environment shifts again. This daily cycle supports safer foraging and movement during the hours of darkness, proving how even small shifts in appearance can greatly enhance survival. Certain snakes, on the other hand, track prey at night by sensing tiny heat signatures. They possess specialized pit organs capable of detecting infrared radiation, a powerful adaptation that lets them locate warm-blooded animals even in complete darkness. The information gathered through these organs includes precise details about direction, distance, and size. Snakes integrate this data with scent trails and subtle vibrations in the ground to build a complete mental picture of their surroundings, allowing them to strike with remarkable accuracy. Even prey that remains motionless, hoping to blend into the night, cannot escape detection, because their body heat contrasts against the cooler environment. Snakes can distinguish between objects warmed by daytime sun and living creatures that generate heat internally, giving them a significant advantage over animals that rely on darkness for protection. This ability also helps snakes navigate terrain where temperature differences shift rapidly, such as rocky areas or forests with varying canopy density. Such sensory adaptations highlight the extraordinary ways nocturnal predators interpret the night. Some moths have evolved astonishing methods to evade bats. They scatter sonar waves in unexpected directions. When a bat sends out a pulsive sound, it reads the returning echo to track prey, but certain moths manipulate the reflection of that sound using specialized wing scales or microscopic structures that distort the echo. Instead of returning a clean signal revealing their location, the sound bounces back in multiple directions, creating confusion for the bat. Sometimes the signal is distorted enough that the bat interprets the moth's position incorrectly, allowing the insect to escape. These moths also perform unpredictable flight maneuvers once they detect the first pulse, exploiting the bat's moment of uncertainty. Because bats hunt at high speeds and depend on extremely precise timing, even a slight delay or misinterpretation can mean a missed opportunity. This evolutionary arms race between predator and prey demonstrates how nocturnal animals develop defenses that directly target their enemies' senses. Certain nocturnal primates rely on unusually flexible neck joints to rotate their heads far beyond the range possible for humans. Living in dense forests where visibility is limited, these primates must detect predators, locate fruiting branches, monitor rivals, and communicate with group members, all while remaining silent and hidden. By rotating their heads at extreme angles without shifting their bodies, they minimize noise and avoid drawing attention. Their large, forward-facing eyes provide exceptional depth perception, essential for navigating the complex network of branches they travel across. When paired with extraordinary head mobility, their visual field expands dramatically. This combination allows them to judge distances accurately, detect subtle movements behind them, and maintain awareness of the canopy around them. The adaptation benefits both survival and social behavior, as it helps primates observe group signals discreetly while staying alert to danger. Meanwhile, many spiders hunt by listening for nighttime echoes through their webs. A spider's web acts as both a physical trap and a sophisticated sensory grid. At night, when sight becomes unreliable, spiders depend on tiny vibrations that travel along the silk. These vibrations reveal detailed information about anything touching or disturbing the web: size, speed, direction, and species of the intruder. Some spiders even detect wind disturbances created by insects flying near, but not touching, the web, allowing them to anticipate a strike. Specialized organs in their legs respond to subtle tension changes in the silk, helping spiders distinguish prey from falling debris or harmless environmental movements. Cooler nighttime air enhances the transmission of these vibrations, making it easier for the spider to interpret them accurately. This system not only increases hunting success but also warns spiders of approaching predators. The web becomes an extension of the spider's sensory world, compensating for limited nighttime vision. Finally, certain nocturnal rodents store seeds at night using memory maps that fade with daylight. They gather food under the cover of darkness to avoid predators, burying seeds in scattered caches across the landscape. Rather than storing these locations as long-term memories, rodents rely on short-lived mental maps based on nighttime landmarks such as shadows, star positions, or shapes illuminated by moonlight. When daylight arrives, these landmarks shift or disappear entirely, causing the memory to fade. This temporary system works because the rodents retrieve most of their food before sunrise. The rapid decay of the memory also encourages efficient collection and prevents repeated visits to the same spots. It reduces the likelihood of exhausting a single area or attracting predators that might track their movements. This strategy showcases how nocturnal animals evolve behaviors suited to the rhythm of night, behaviors that depend on temporary information, fleeting signals, and a world that transforms completely with the coming of dawn. Nocturnal ecosystems operate on delicate timings and subtle sensory cues, and many species have evolved remarkable nighttime behaviors to survive in conditions where light is scarce, competition is high, and predators rely on the slightest signals to detect prey. And one example of this complexity can be seen in the rodents whose fading memory maps not only prevent predators from following predictable patterns but also force the rodents to choose new storage sites each night, ensuring their resources remain spread across wider areas rather than concentrated in a few vulnerable spots, thereby reducing the chances of losing everything to a single competitor, changing weather event, or environmental disruption, a strategy especially efficient for species facing intense predation pressure in open spaces where lingering too long during daylight can prove fatal, and much like these rodents. Certain bats also display extraordinary adaptations during nighttime activity because when many bats forage together in an area, their echolocation calls often overlap and blend into a confusing acoustic mix that makes it difficult for each individual to interpret echoes accurately. So to solve this problem, some species rapidly switch frequencies upon detecting other bats nearby, creating distinct acoustic channels that separate their signals and prevent interference. And this adjustment takes place within a single hunting pass, enabling multiple bats to pursue the same insect swarm simultaneously without colliding or confusing their own signals with those of their neighbors, demonstrating astonishing auditory awareness and split-second adaptability as they continuously monitor the shifting soundscape while maintaining precision. And owls, another group of nocturnal specialists, exploit sensory asymmetry in ways that defy typical anatomical expectations because some species possess asymmetrical ear placement, with one ear positioned higher than the other, allowing their brains to compare slight differences in sound arrival time and intensity to pinpoint prey in three-dimensional space with astonishing accuracy, even when a mouse is hidden beneath layers of snow, thick vegetation, or loose soil. And this vertical and horizontal spatial awareness, combined with the quiet of nighttime environments, enables them to hunt with minimal wasted energy, striking with precision that leaves almost no room for error. And similarly, nocturnal cats widen and narrow their pupils with exceptional speed to catch the faintest movements in low-light environments. When their pupils widen, more available light reaches the retina, dramatically increasing sensitivity, while narrowing reduces glare from reflective surfaces or artificial lights, and paired with reflective layers behind the retina known as the tapetum lucidum. These adjustments form a visual system capable of detecting slight shifts in shadow or motion that would go entirely unnoticed by many animals, supporting stealthy movement, coordinated stalking, and an overall awareness suited for near darkness. While in moisture-dependent species such as certain toads, night becomes a navigational advantage because they travel long distances guided not by sight but by humidity gradients that shift predictably after sunset, following subtle moisture differences that lead them toward water or food while avoiding dry paths that could dehydrate them. And this ability to sense humidity also helps them evade visually oriented predators by restricting movement to hours when cooler temperatures and higher moisture allow them to cover large areas safely. And some nocturnal birds adapt to the challenges of nighttime flight by flying lower to avoid strong and unpredictable winds at higher altitudes, benefiting from more stable airflow and ground-level cues that replace visual landmarks lost in the dark sky, reducing energy expenditure and improving safety from airborne predators that patrol higher altitudes. While certain lizards restrict activity to moonless nights when the absence of moonlight provides maximum cover from aerial predators, allowing them to forage, mate, and relocate between shelters using senses not dependent on light, while blending into pooled shadows cast by earth and vegetation. A strategy that also reduces competition from species active during brighter conditions and conserves water because lower temperatures limit evaporation, and in the ocean, certain sharks hunt after sunset using specialized light-sensing cells along their snouts that detect small changes in brightness when objects pass overhead, translating subtle variations in scattered light into cues that reveal the presence of prey even when the water is dark, murky, or turbulent. And because surface light fades unevenly at dusk, these gradients often become sharper at night, making motion more obvious than during daylight hours, allowing sharks to track even still or slow-moving animals with immediate precision before combining that sensory input with smell, water pressure detection, and efficient swimming patterns that keep them aligned with disturbances in the water column. And returning to terrestrial environments, some rodents leave scent marks that glow faintly under moonlight, not bright enough to reveal them to predators but clear enough to individuals with the required visual sensitivity, creating navigational guides that confirm safe routes without relying solely on memory, enabling them to move quickly between feeding grounds, shelters, and group members with minimal hesitation. While the chemical composition of these marks reflects moonlight differently than surrounding surfaces, producing a soft contrast detectable even when shadows shift unpredictably under branches or grasses. And because the glow fades gradually, the rodents avoid overusing the same paths, which would otherwise increase exposure to predators or competitors. In this world where every moment of darkness shapes behavior, adaptation becomes essential for survival. And each species, from bats adjusting frequencies in milliseconds, to owls mapping sound in 3 dimensions, to cats fine-tuning their pupils, to toads navigating by humidity, to lizards timing emergence to moon cycles, to sharks reading faint ambient light, to rodents following glowing scent trails, demonstrates that night is far from silent or passive but instead an intricate landscape defined by fleeting signals, environmental patterns, shifting sensory cues, and evolutionary brilliance, illustrating how life thrives not by resisting darkness, but by understanding and using it with remarkable precision. Nocturnal life depends on constant adaptation, and much of this adaptation occurs in forms so subtle that they remain invisible to daytime observers, Yet these mechanisms shape survival in profound ways, beginning with rodents that combine faint visual cues and chemically marked trails to move through complex nighttime landscapes without falling into predictable patterns that predators could exploit. Because each scent they leave is deliberately faint and positioned in ways that disperse over time, preventing long-term tracking while still offering enough guidance for rapid navigation across uneven terrain, shifting shadows, and low-light conditions. And together these combined cues form a flexible map that can be updated each night, giving the rodents a dynamic understanding of their environment rather than relying on a rigid, easily exploited routine. This interplay between sensory input and environment reveals how even small animals must constantly reimagine their routes to face ever-changing nocturnal conditions. And just as rodents use delicate sensory strategies to travel, bats rely on social warmth and synchronized behavior long before they take their first winged beat of the night, gathering in tight clusters deep inside roosts where temperatures often fall dramatically, because their thin wing membranes, which are essential for aerodynamic maneuverability, lose heat far more quickly than fur-covered bodies, thus prompting many species to huddle tightly to share warmth, maintain stable body temperature, reduce heat loss through drafts moving through caves or tree hollows, and ensure that each individual conserves enough energy to power the rapid muscle contractions required for hunting insects, navigating long distances, or performing complex aerial maneuvers. And these roosting clusters also serve secondary functions such as strengthening social bonds, increasing safety from predators that may intrude into their shelters, and facilitating efficient communication as individuals exchange cues that coordinate nightly departures, all of which demonstrates that thermoregulation in bats is as much a social endeavor as it is a physiological one. While bats fine-tune their internal temperatures before emerging, certain insects look to the sky for navigation, reading polarized moonlight, a pattern invisible to humans yet stable and reliable even when cloud cover or shifting atmospheric conditions scatter brightness, allowing them to maintain straight paths over long distances across landscapes with few distinguishing features, such as deserts, grasslands, or open water, where ground-level cues may be repetitive or easily confused. And this remarkable ability to interpret polarization patterns enables insects to travel with precision, avoid unnecessary circling, prevent energy waste, and quickly locate feeding grounds or nesting sites, offering an elegant solution to the navigational challenges faced by small nocturnal species that rely on the faintest signals nature can provide. Similarly, amphibians take advantage of nighttime climatic shifts by relying heavily on fog to maintain hydration, as the rapid cooling of air after sunset allows moisture to condense into fine droplets that settle along vegetation, rocks, and soil, creating temporary microhabitats where moisture-dependent animals can remain active without the risk of dehydration. And these amphibians often position themselves where fog collects most densely, reducing the need to travel long distances in search of open water while simultaneously masking their scent from predators that hunt using smell. And this synchronization between environmental conditions and behavior demonstrates how essential timing is for species whose skin absorbs water directly from the atmosphere, because even slight changes in humidity influence their movement, feeding, and survival. Meanwhile, certain snakes shift their sensory priorities dramatically after dark, reducing reliance on scent and vision, which become less effective in cooler nighttime air, and increasing sensitivity to ground vibrations that travel through soil, leaf litter, or rocks, using specialized jawbones and muscle structures as vibration receivers capable of detecting even faint disturbances produced by small animals moving beneath vegetation, within burrows, or across the forest floor, allowing the snakes not only to locate prey with remarkable precision but also to detect approaching predators or large animals. And this nightly sensory recalibration gives snakes a significant advantage in environments where visibility and airborne chemical dispersion fluctuate unpredictably. Nocturnal mammals also respond to changes beyond the immediate environment, timing their foraging behaviors around lunar cycles, with many species reducing activity during bright moonlit nights when predators can spot them easily, instead choosing the darker phases of the moon when shadows merge and concealment increases. And these rhythms influence interspecies interactions as different animals adjust their schedules to minimize competition and avoid unnecessary encounters, while some mammals even coordinate group movement or shared feeding behaviors according to predictable moon phases, ensuring that energy is not wasted navigating brightly lit forests where cautious movement slows feeding efficiency. And among the most iconic nocturnal hunters, owls rely on anatomy specially evolved for low-light vision, using reflective tissues behind the retina to send incoming photons back through the photoreceptors a second time, greatly increasing the likelihood that even the faintest glimmer of movement will be detected. And although this adaptation does not create bright or detailed images, it dramatically improves sensitivity, allowing owls to navigate through dense forests full of unpredictable shadows while tracking prey that blends seamlessly into the dark ground. And, when combined with large eyes, wide pupils, and highly specialized neural pathways for processing visual information, this feature supports precise flight and exceptional hunting accuracy. Amphibians such as certain frogs also modify their nighttime activities in extraordinary ways by adjusting their calls to account for temperature-dependent changes in sound transmission, altering pitch, rhythm, and spacing to maintain clarity for potential mates or rivals even as cool air changes how sound waves travel, ensuring their signals do not distort or fade across distance. And because vocal communication plays a central role in reproductive success for many species, these moment-by-moment adjustments help conserve energy while keeping communication effective under shifting environmental conditions. In addition, some nocturnal insects rely heavily on touch rather than sight, using antennae, sensory hairs, and delicate leg structures to build internal maps of their surroundings as they navigate through dense vegetation, narrow tunnels, cluttered forest floors, or underground networks where light cannot penetrate. And although this touch-based approach may be slower than visual navigation, it provides unmatched reliability regardless of weather, moonlight, or environmental disturbances, offering consistent safety from predators while enabling accurate exploration and feeding. Finally, several bat species display extraordinary aerial adaptability by reshaping their wings mid-flight to avoid obstacles they cannot see, using flexible joints and thin, responsive membranes capable of altering curvature within milliseconds as changes in airflow signal the presence of trees, cavern walls, cliff edges, or other bats. And these constant adjustments allow them to maneuver through forests, caves, or narrow canyons with astonishing precision, performing rapid turns and sudden shifts in direction without sacrificing speed or stability, revealing the incredible biomechanics that underlie each seemingly effortless movement. And taken together, all these nocturnal behaviors, from scent-based rodent mapping to bat clustering, from polarized light navigation to fog-dependent hydration, from vibration-sensitive hunting to lunar-timed foraging, from reflective-eyed owl vision to temperature-tuned frog calls, from tactile insect navigation to aerodynamic bat agility, form a vast interconnected tapestry of adaptations that illustrate how life after sunset is shaped by fleeting signals, shifting atmospheric conditions, subtle sensory cues, and the ever-changing patterns of darkness that guide the movements, decisions, and survival strategies of species that thrive where light is scarce. Their ability to sense slight shifts in air movement allows them to detect branches, walls, or other obstacles before touching them, an essential skill because their echolocation pulses do not always reach every surface in time to prevent sudden impacts. And by combining sound-based awareness with mechanical feedback from the air, bats maintain high-speed maneuverability in complete darkness, reshaping their wings to adjust lift and drag for sharp turns or rapid climbs as they pursue insects that move unpredictably. This coordination between sensory systems and physical structure reveals that their wings act not only as engines of flight but also as active sensors that enhance nighttime navigation. Certain rodents whisper ultrasonic calls far above human hearing, communicating information about threats, food, and social behavior through frequencies that most predators cannot detect, giving them a secure private channel. The short-range signals keep communication within the group, reducing the chance of interception. And the rodents produce these calls with specialized vocal structures while relying on precisely tuned receptors in their ears, allowing them to coordinate movement during group foraging without using scent trails or visual cues in dense vegetation. Some cats use whisker sensitivity to read air currents in complete darkness, with each whisker acting as a finely tuned sensor detecting subtle disruptions in airflow so they can sense obstacles and track silent prey without touching or seeing them. The whiskers connect to fast processing nerve clusters that allow immediate adjustments in movement, supporting silent progress through complex environments, and helping them track motion behind or below them without shifting their heads. Demonstrating how nocturnal mammals integrate many sensory systems for precision. Many birds migrate at night to avoid overheating under the daytime sun, taking advantage of cooler temperatures, calmer winds, and reduced predator exposure while navigating by stars, magnetic fields, and wind patterns. Traveling during nighttime allows continuous progress without heat stress and leaves daylight hours available for feeding to rebuild energy reserves. Showing how birds align migration timing with environmental cycles to balance safety, endurance, and resource availability. A number of geckos climb smooth surfaces in darkness using microscopic hairs that branch into extremely fine tips interacting with surfaces through weak electric forces, creating reliable grip even on glass or metal. Because visual depth cues fade at night, this adhesion system becomes crucial, and geckos adjust foot pressure smoothly, resetting their grip quickly without sticking permanently or collecting debris. Enabling silent, efficient climbing in search of insects or escape routes. Inaccessible to other animals. Certain shrimp turn nearly transparent at night as pigments disperse through their bodies, reducing their color and blending them with the shifting underwater light, making it difficult for predators to detect them. The low illumination of nighttime amplifies this camouflage, especially during periods of movement such as feeding or migrating. And the effect reverses at daylight when stronger illumination requires different defense strategies, showing how aquatic animals adapt visibility to match changing conditions. Some fish rise from deeper layers after dark to feed safely near the surface, avoiding daytime predators that rely on vision. The nighttime coolness alters prey behavior and makes them easier to catch, but ascending requires careful timing because the conditions that draw prey also draw predators, so the fish rely on cues such as temperature gradients and lowering light levels to decide when it is safe to move upward. Animals that navigate, feed, migrate, communicate, and survive under the cover of darkness rely on a broad range of specialized behaviors shaped by environmental pressures, sensory limitations, and predictable natural cycles, and many species demonstrate remarkably intricate patterns of nighttime activity that reveal how life has adapted to the challenges and opportunities of reduced illumination. Once certain fish rise near the surface after sunset, they move efficiently through zones rich in plankton or small drifting organisms, using their highly sensitive eyes, which adapt to low light far more effectively than those of many daytime predators. These predators, accustomed to bright environments, struggle to see clearly after twilight, giving nocturnal foragers a distinct advantage as they sift through shifting currents of nutrients and suspended life. After feeding, these fish descend again into deeper layers well before sunrise, regaining the protection that darker waters provide and ensuring that they avoid the renewed appearance of visually skilled hunters that emerge with daylight. This daily vertical migration supports energy balance, reduces predation risk, and demonstrates that depth is not a fixed habitat but a dynamic resource that animals use strategically according to changing conditions. Similarly, certain crabs restrict their foraging activities to nighttime hours in order to avoid the harmful ultraviolet radiation that intensifies under direct sunlight and poses a threat to many crustaceans by damaging delicate tissues. Ultraviolet exposure grows especially intense in shallow coastal zones where these crabs hunt. So darkness becomes a protective shield that allows them to roam open ground more freely while relying on sensitive touch and chemical cues to locate food buried beneath sand, hidden under stones, or concealed inside small crevices. This nighttime schedule also reduces encounters with visually oriented predators that dominate shallower waters during the day, and because many prey species become active shortly after sunset, the crabs experience an increase in food availability exactly when the environment is safest. This alignment of feeding time with environmental conditions illustrates how radiation levels shape the timing of essential survival tasks, and how many organisms adapt their behavior to daily shifts that reliably repeat over months, years, and evolutionary timescales. Some mammals also structure their entire daily rhythm around nighttime conditions, resting through the day to conserve energy for demanding hunts that require bursts of speed, precise coordination, and extended movement that would be far more exhausting under hot daylight temperatures. Resting while the sun is high allows these animals to regulate body temperature more effectively, avoid unnecessary stress, and protect themselves from predators that are more active during the day. When night arrives, cooler air, reduced competition, and increased prey activity create an ideal window for hunting, and these mammals rely on acute hearing and enhanced sense of smell to compensate for limited light, allowing them to track subtle rustles, faint scents, and tiny movements of hidden prey. This schedule ensures that they maintain strong energy reserves for tasks that demand focus and endurance. And it demonstrates how mammals fine-tune their routines to match predictable patterns of safety, temperature, and food availability. Salamanders take advantage of humid nights by absorbing oxygen directly through their skin, a method of respiration that depends on moisture levels in the surrounding environment. Humidity keeps their skin moist enough for oxygen to diffuse into the bloodstream, enabling these animals to remain active without relying fully on lungs, which are less efficient during slow movement or when they must remain extremely still. On dry or windy nights, this method becomes less effective, prompting salamanders to shelter beneath logs, inside wet soil, or under dense vegetation until moisture levels rise again. But once humidity increases, they emerge to forage, search for mates, and move quietly through forests, wetlands, and shaded areas where water accumulates naturally. The reliance on environmental moisture highlights how external conditions determine their activity patterns and how their delicate skin imposes specific behavioral constraints that must be navigated carefully each night. Some insects, navigating the darkness of enormous landscapes, use a surprisingly sophisticated strategy by tracking the slow rotation of the night sky. They rely on bright groups of stars rather than individual points of light, recognizing broad celestial patterns that shift at a predictable rate, and use these patterns to maintain a consistent direction during long nighttime flights across plains, deserts, or grasslands where ground-level landmarks fade into shadow. As the night progresses and the sky rotates overhead, these insects compensate for the shifting position of star patterns, ensuring they do not circle back over the same terrain or waste precious energy wandering in an unintended direction. The strategy reduces disorientation caused by wind, terrain, or changing shadows and illustrates how even small animals can use enormous-scale environmental information to accomplish complex navigational tasks essential for survival. In regions where hunting pressure is high and many individuals gather in the same airspace, certain bats avoid sensory confusion by dividing their environment into sound-based territories. When many bats emit echolocation pulses at once, overlapping signals can blend together and make it difficult for individuals to distinguish echoes from their own calls. To prevent this interference, the bats actively monitor the acoustic landscape and adjust their position by flying at different heights, choosing separate horizontal lanes, or altering the pitch of their calls so that each bat occupies a distinct auditory channel. These dynamic, shifting sound territories allow multiple bats to exploit the same insect swarms without disrupting each other's tracking abilities and reduce the likelihood of mid-air collisions during intense hunting sequences. This coordination demands constant awareness, rapid adjustment, and a complex understanding of how sound interacts in shared space, demonstrating that nocturnal animals often rely on sensory management rather than physical boundaries to avoid conflict. Some mice enhance their nighttime survival by adopting zigzag escape patterns that confuse predators. Pursuit hunters tracking prey at night rely heavily on movement patterns rather than clear visual outlines, and a mouse that flees in a straight, predictable line becomes an easy target. Instead, by darting unpredictably left and right, varying the length and speed of each sprint, and using vegetation as occasional cover, mice disrupt the predator's ability to predict trajectory, forcing constant recalculation and creating tiny delays that may be just enough for the mouse to reach shelter. This survival strategy requires coordination rather than strength or speed and demonstrates how small animals compensate for physical vulnerability through unpredictable motion that undermines a predator's decision-making process. Certain owls further refine their nighttime strategies by coordinating their hunting success with lunar cycles. Moonlight changes how prey behave, with many small animals reducing their movement on bright nights to avoid detection. In response, some owls adjust their tactics by shifting to areas with dense cover, altering perch height, beginning their hunts earlier or later, or expanding their search radius when darkness encourages prey to travel more confidently. This synchronization with lunar brightness ensures that the owls remain effective hunters regardless of changing visibility and demonstrates how nocturnal predators must understand and adapt to recurring celestial patterns that influence prey behavior, landscape, brightness, and risk levels. Meanwhile, certain amphibians glow faintly under moonlight due to natural pigments in their skin that react to ultraviolet components in lunar illumination, producing a subtle luminescence visible only at close range. The glow does not brighten the environment or attract undue attention but instead serves as a quiet form of communication that allows individuals to recognize potential mates or group members without relying on vocalizations that might reveal their presence to predators. Because the effect appears only under dim lighting, amphibians remain safe from daytime hunters with stronger visual acuity, and the slight variations in glow between individuals may convey information about health, maturity, or readiness for mating. This adaptation is especially valuable in environments where dense vegetation, water reflections, and shifting shadows make visual identification difficult. Together, these behaviors, vertical migrations, ultraviolet avoidance, rest-driven hunting schedules, moisture-dependent respiration, celestial navigation, sound-based territorial spacing, zigzag escape strategies, lunar synchronized predation, and subtle bioluminescent communication, form a sweeping tapestry of nocturnal adaptation that demonstrates how countless species, across land, water, and sky, make use of environmental rhythms, atmospheric conditions, and sensory specialization to thrive. In darkness where danger, challenge, and opportunity coexist in delicate balance. Certain moths demonstrate a remarkable ability to detect the scents of night-blooming flowers over long distances, relying on their highly sensitive antennae, which contain specialized receptors capable of picking up incredibly low concentrations of odor molecules dispersed through the cool nighttime air, allowing them to locate resources that are entirely invisible in darkness. Flowers that bloom at night often emit stronger or more distinctive scents specifically to attract these nocturnal pollinators, and as moths fly, they interpret subtle changes in the intensity and direction of the odor, constantly adjusting their flight path to move toward the source, following chemical gradients that guide them across varied terrain. Once they reach a flower, the moths combine tactile sensing with chemical detection to precisely locate nectar hidden deep within the petals, creating a mutually beneficial system in which the moths obtain nourishment while simultaneously pollinating the plant, demonstrating the critical role of chemical communication in nocturnal ecosystems and highlighting how life in darkness evolves strategies independent of visual cues. Many predators, in contrast, shift their sensory priority from vision to hearing after sunset because shadows distort outlines and low light diminishes visual clarity, forcing them to rely on the subtle auditory cues produced by prey, including rustling leaves, snapping twigs, or the soft scuff of movement across soil. To exploit these faint signals, nocturnal hunters possess highly tuned auditory systems that amplify relevant sounds while filtering background noise, allowing them to move cautiously, pause frequently, and adjust posture to reduce the noise of their own movements, all of which enables them to detect prey that attempt to freeze in place as a defense. This reliance on sound ensures successful navigation and hunting even when visual information is unreliable and illustrates the essential role of sensory flexibility in the survival strategies of nighttime predators. Certain rodents extend this ingenuity into celestial navigation, memorizing star patterns from previous nights and using them as a reference to maintain direction when emerging from their shelters. By comparing the current positions of star clusters to their stored mental maps, these small mammals traverse open areas devoid of stable landmarks, moving efficiently between feeding grounds and safe shelter. They do not rely on exact star positions but recognize general arrangements, which remain relatively constant over short periods, and this method becomes particularly important during moonless nights when terrestrial cues are entirely absent, demonstrating that even small mammals integrate large-scale environmental information into their survival strategies. Birds that migrate at night employ similar energy-saving adaptations, lowering their heart rates to conserve oxygen and reduce metabolic demand during long flights, a strategy facilitated by cooler nighttime temperatures that enhance heat dissipation. This combination of physiological control, stable wind patterns, and reduced predation risk allows nocturnal migrants to travel long distances without frequent stops, preserving energy for critical portions of their journey, such as crossing open water or reaching resource-rich stopover sites, while maintaining enough power to adjust for unexpected gusts or obstacles. Nocturnal insects also employ sound-based strategies for survival and competition, including mimicking predator noises to deter rivals. In the darkness, when visibility is limited, these acoustic signals provoke retreat and submission, enabling the mimic to claim feeding territories or mating opportunities without engaging in energy-intensive physical confrontations. The effectiveness of such mimicry is amplified in dense habitats, where sound reverberates unpredictably, creating illusions of larger or faster predators and further conserving energy while maintaining control over resources. Owls hunting at night employ extraordinary flight mechanics, using broad wings and slow, controlled wing beats to hover silently above potential prey, maintaining a stable position while observing subtle movements beneath dense vegetation. This hovering ability allows them to patiently wait for prey that pauses frequently, and their specialized feathers minimize vibration and channel airflow smoothly, reducing sound and allowing precise, rapid strikes when the opportunity arises. Similarly, bats coordinate group hunts through brief mid-air signals that inform nearby individuals of each bat's position without revealing their location to predators, allowing the group to cover insect swarms efficiently while avoiding collisions and redundant effort, with calls functioning as rapid status updates that maintain social awareness and optimize foraging efficiency in a three-dimensional, rapidly changing nocturnal environment. Rodent colonies also structure their nocturnal activity strategically, emerging from burrows in organized waves to forage collectively under cover of darkness, relying on tactile, olfactory, and low-frequency auditory signals to communicate and coordinate, maintaining territorial control and minimizing exposure to visually oriented predators. These colonies remain mostly inactive during the day, conserving energy and avoiding heat stress, while their interconnected burrows or nests maintain stable temperatures that support daytime rest. Across the animal kingdom, these behaviors reflect a deep integration of physiology, behavior, and environmental awareness, as nocturnal animals rely on chemical gradients, auditory cues, celestial patterns, energy management, sound mimicry, precise flight mechanics, and social coordination to navigate, hunt, forage, and communicate in low-light conditions. By adjusting heart rate, exploiting humidity, tracking stars, manipulating chemical signals, and calibrating complex sensory inputs, nocturnal animals optimize survival under predictable daily cycles of darkness and light. Moths, owls, bats, rodents, insects, birds, and other species illustrate the richness of life adapted to nighttime conditions, showing how evolution sculpts sensory systems, motor skills, and social strategies to exploit opportunities invisible to diurnal species. These adaptations are interconnected, as the precise timing of activity, the conservation of energy, and the accurate interpretation of environmental information collectively determine success in the night. Chemical communication allows nocturnal foragers to find food despite poor visibility. Auditory specialization guides predators in tracking prey. Celestial navigation ensures accurate travel across featureless terrain. And energy-saving physiological adjustments enable sustained flight or movement without exhaustion. Social and acoustic strategies enhance coordination among individuals, while mimicry and stealth tactics reduce conflict and predation risk. The nocturnal landscape is thus a carefully balanced environment in which every sensory and behavioral adaptation increases the probability of survival, reproduction, and resource acquisition. Whether through hovering silently, tracking faint odor plumes, memorizing star patterns, or synchronizing group activity, nocturnal animals exhibit remarkable ingenuity, blending physiology and behavior with environmental knowledge to thrive under the constraints of darkness. From moths guided by scent to owls refining aerial precision, from bats communicating through sound to rodents navigating by celestial memory, These strategies collectively illuminate the extraordinary ways in which life on Earth has evolved to function efficiently when light is scarce, demonstrating that darkness is not a limitation but a domain full of opportunities that reward those capable of exploiting its unique patterns and rhythms, and that nocturnal adaptation is simultaneously a reflection of environmental pressures, evolutionary innovation, and the delicate choreography of life that unfolds silently every night across the planet, where predators, prey, and pollinators coexist in a web of interactions mediated by sound, smell, sight, touch, and even moonlight, revealing the depth and complexity of ecosystems thriving beyond human perception and underscoring the remarkable resilience and ingenuity inherent in life adapted to the rhythms of the night. The faint glow observed in certain amphibians under dim moonlight serves as a subtle communication tool, allowing individuals to interpret social cues such as the presence of potential mates, rivals, or group members without exposing themselves to unnecessary danger, and this adaptation highlights how seemingly minor physiological traits can play a critical role in survival within low-light habitats, enabling these animals to convey information discreetly while remaining largely invisible to predators. Similarly, certain moth species exhibit an extraordinary ability to detect the scents of night-blooming flowers across long distances, relying on highly sensitive antennae equipped with specialized receptors capable of perceiving even the smallest concentrations of chemical molecules dispersed through the cool nighttime air, which allows them to locate nectar sources that are otherwise invisible in the dark. And flowers that bloom after sunset often produce stronger or more distinctive scents, specifically to attract these nocturnal pollinators. As moths navigate toward these odor sources, they interpret subtle changes in scent intensity and adjust their flight paths accordingly, following chemical gradients that guide them over complex terrain, and upon reaching the flower, they use a combination of tactile sensing and olfactory perception to locate the nectar precisely, facilitating a mutually beneficial relationship in which the moths receive nourishment while simultaneously pollinating the plants, demonstrating the indispensable role of chemical communication in nocturnal ecosystems, and the ways in which life evolves to exploit non-visual cues. Nocturnal predators, in turn, often rely more heavily on sound than on sight, since darkness diminishes visual clarity and shadows distort the outlines of prey, forcing these hunters to adapt by focusing attention on auditory information, such as rustling leaves, snapping twigs, or the faint scuff of movement across soil. Their auditory systems are finely tuned to amplify subtle noises while filtering out irrelevant background sounds, allowing predators to move cautiously, pause strategically, and adjust their posture to avoid masking critical cues, which enables them to detect prey that attempts to remain motionless to avoid detection and to navigate safely through terrain where visibility is unreliable, illustrating the importance of sensory flexibility for nocturnal success. Certain rodents also incorporate celestial navigation into their behavioral repertoire, memorizing star patterns from previous nights to create mental maps that guide movement when terrestrial landmarks are absent, allowing them to move efficiently between feeding grounds, nesting areas, and safe shelters. These animals do not rely on exact positions of individual stars but rather recognize general constellations and arrangements that remain relatively constant over short intervals, which proves particularly valuable during moonless nights when terrestrial cues are minimal or absent, demonstrating that small mammals can integrate large-scale, consistent environmental information into their navigation strategies to maintain orientation and conserve energy. Similarly, migratory birds flying at night employ physiological adaptations to optimize energy use, such as lowering their heart rates to reduce oxygen consumption and metabolic demand during long-distance flights, while cooler nighttime temperatures facilitate heat dissipation, enabling sustained flight without the frequent need to stop and feed. This combination of physiological regulation, stable nocturnal wind patterns, and reduced predator presence allows birds to cover vast distances efficiently, while still maintaining sufficient power for rapid maneuvers or altitude adjustments, illustrating how tightly controlled internal processes support survival during long migratory journeys and ensure energy is available for critical stages, such as crossing open water or reaching resource-rich stopover sites. Insects, too, exploit the limitations of nocturnal environments, with some species mimicking predator noises to manipulate the behavior of rivals, by producing sounds that resemble the calls or movement patterns of predators. These insects induce retreat in competitors, allowing the mimic to claim feeding territory or mating opportunities without engaging in energy-costly confrontations. This acoustic mimicry is especially effective in dense habitats, where echoes and reflections enhance the perceived size or speed of the supposed predator, allowing the insects to conserve energy while maintaining access to critical resources, showcasing the sophisticated ways in which nocturnal animals manipulate sensory-dependent behaviors within their ecosystems. Owls hunting at night demonstrate extraordinary aerial adaptations, using broad wings and slow, deliberate wing beats to hover silently above prey while maintaining precise stability, allowing them to remain nearly motionless in the air as they observe small mammals moving below, a skill particularly useful in environments where prey pause frequently. And sound control is critical because many prey species rely more on hearing than sight for detecting danger. The owl's feathers minimize vibration and channel airflow smoothly, enabling subtle positional adjustments in response to auditory or visual cues, and when the moment is optimal, the owl drops swiftly and silently to capture prey with precision, highlighting how nocturnal predators refine flight mechanics to overcome the challenges posed by low-light hunting. Bats display an additional level of social sophistication during nocturnal hunts, coordinating group foraging through brief, high-frequency mid-air calls that do not reveal hunting locations to predators but allow individuals to gauge the positions of nearby bats, avoid duplicating effort, and efficiently cover areas dense with insect prey. These specialized calls function as rapid status updates rather than traditional echolocation signals, permitting the group to adjust dynamically to changes in prey distribution, minimize collision risk, and optimize collective foraging efficiency, demonstrating social awareness and fast decision-making in highly mobile nocturnal animals. Many rodents organize themselves into colonies that are primarily active during night hours, structuring movement, feeding, and communication to occur after sunset in order to reduce exposure to predators that rely on sight. Within these colonies, members coordinate using scent, tactile cues, and low-frequency sounds, emerging in waves to gather resources without overwhelming local food sources, and collectively responding to threats while defending shared territory, while the nocturnal schedule ensures energy conservation and avoidance of heat stress during the day, with interconnected burrows or nests maintaining stable temperatures. The rhythm of nighttime activity also shapes social interactions, influences resource sharing, and demonstrates how rodent group living adapts to nocturnal pressures, balancing cooperation with the need for stealth and efficiency, while across multiple taxa, from amphibians communicating with subtle bioluminescence to moths tracking floral scents. From nocturnal predators relying on sound to birds adjusting physiology for energy-efficient flight, these behaviors illustrate a remarkable array of evolutionary adaptations that enable animals to survive and thrive in low-light conditions. Nocturnal life demands integration of multiple sensory inputs, careful energy management, and coordinated social strategies, as chemical cues guide foraging. Auditory and tactile inputs facilitate hunting and navigation, celestial patterns support orientation, and physiological adjustments allow sustained activity without exhaustion. Predators, prey, pollinators, and social animals all demonstrate the creative ways evolution has shaped behavior, morphology, and physiology to exploit the unique conditions of darkness, revealing that nighttime is not merely a time of reduced activity but a rich domain filled with opportunities that reward specialization and adaptability. These interlinked adaptations reflect the interplay of environmental constraints, sensory capabilities, and social coordination, forming complex systems that balance survival, reproduction, and resource acquisition. Whether through hovering silently, tracking faint odor plumes, memorizing star formations, mimicking predator cues, coordinating mid-air hunting, or structuring group activity, nocturnal animals collectively show how life adapts to the rhythms of darkness, exploiting non-visual cues, energy-efficient strategies, and social intelligence to navigate and thrive. The night becomes a dynamic landscape of opportunities, where chemical, auditory, and visual subtleties guide movement and behavior, where energy must be conserved yet deployed strategically, and where social and ecological interactions unfold in ways invisible to diurnal observers. Each adaptation, from the delicate antennae of a moth to the precise wing mechanics of an owl, from celestial navigation in rodents to acoustic mimicry in insects, demonstrates the intricate balance of form, function, and environment that defines nocturnal survival. Collectively, these behaviors illustrate a profound evolutionary truth. Darkness is not an obstacle but a selective pressure that fosters innovation, coordination, and efficiency, and the nocturnal world is a testament to the ingenuity of life, where survival depends on the seamless integration of sensory perception, behavioral strategy, physiological optimization, and social interaction, creating ecosystems that operate on rhythms, cues, and dynamics entirely distinct from the daylight world, yet equally complex and finely tuned to the demands of life after sunset. To manage the risks of predation and extreme environmental conditions, many nocturnal rodents remain deep inside burrows during daylight hours where temperatures remain relatively stable, providing insulation from sudden heat spikes and creating safe zones where they can rest, groom, and store food. These subterranean refuges serve as both protective shelters and thermal regulators, ensuring that the animals maintain hydration and energy balance during the harshest parts of the day. When night arrives, the rodents emerge to forage, taking advantage of cooler air, reduced competition, and decreased predator activity. Their nighttime activity depends on careful timing, as they begin to search for food only when surface temperatures fall to levels that prevent rapid moisture loss and minimize stress on their bodies. The burrow systems often feature multiple entrances and interconnected tunnels, allowing quick retreats if danger approaches, and enabling the animals to move freely within the safety of their underground network while avoiding exposure to predators. These rodents navigate using a combination of scent trails, spatial memory, and low-intensity acoustic cues that are barely perceptible to others, demonstrating a sophisticated integration of sensory information adapted to low-light environments. This strategy illustrates the intricate relationship between shelter, schedule, and survival in nocturnal species, as the animals balance energy conservation with the need to forage efficiently in unpredictable and often harsh conditions. Similarly, certain nocturnal birds possess the ability to detect subtle shifts in air pressure to locate prey under the cover of darkness, using highly sensitive receptors that perceive minute disturbances caused by wing beats or movements of insects and small mammals. These birds integrate this information with their low-light vision and acute hearing, forming a multi-layered detection system that allows them to approach prey with precision, adjusting flight speed, angle, and approach path in response to environmental cues. Air pressure sensitivity offers a significant advantage in cluttered habitats, where echoes, shadows, and vegetation can otherwise obscure visual cues, while simultaneously enabling the birds to monitor wind currents and maintain stability during nocturnal flight. The combination of physiological adaptation and refined sensory perception highlights the ways in which nocturnal species evolve specialized traits to exploit conditions that remain challenging for diurnal animals. Among insects, many amplify faint nighttime sounds through complex auditory organs composed of membranes, internal chambers, and specialized structures that enhance weak signals, allowing them to detect predators, rivals, and potential mates with remarkable sensitivity. In the cooler, quieter nighttime environment, these amplified signals become critical sources of information, guiding movement, social interactions, and survival strategies in conditions where vision offers limited support. By interpreting subtle acoustic patterns affected by humidity, wind, and vegetation density, these insects adjust their behavior dynamically, moving to new locations, modifying signaling strategies, or remaining still to avoid detection, demonstrating that advanced auditory processing is not confined to larger animals and can be essential for small nocturnal species operating in complex environments. Certain frogs, meanwhile, produce a soft, natural glow under starlight through fluorescence caused by skin pigments that absorb specific wavelengths of light and re-emit them as faint illumination. This subtle glow enables communication at close range without vocalization, allowing frogs to recognize individuals, signal reproductive readiness, or maintain spatial arrangements within a group while remaining largely invisible to visually oriented predators. The glow becomes particularly effective under starlight, when stronger ambient light is absent, and it provides a safe, energy-efficient alternative to vocal calls that could otherwise attract competitors or threats, illustrating the creative ways nocturnal animals use natural physics to convey information under restrictive conditions. Many mammals employ physiological strategies to conserve energy during night activity, lowering body temperature to reduce metabolic demand and stretch limited energy reserves in the face of fluctuating food availability. This controlled reduction in temperature allows extended periods of activity without frequent feeding while maintaining sufficient responsiveness to detect predators and forage effectively. These mammals carefully regulate movement, breathing, and muscle activity to match their reduced metabolism, selecting sheltered locations that mitigate temperature loss and gradually restoring full body temperature when preparing for active tasks. This form of internal regulation highlights how nocturnal animals integrate physiology and behavior to maximize survival in environments where resources are variable and conditions are challenging. Similarly, certain reptiles exploit thermally buffered microhabitats, such as sun-warmed rocks, to maintain activity after dark. Unable to generate sufficient internal heat independently, these reptiles rest on surfaces that have absorbed daytime warmth, allowing muscle function, alertness, and digestive processes to continue efficiently into the night. The selection of specific rocks based on shape, orientation, and heat retention becomes a critical behavioral adaptation, influencing territorial choices and feeding patterns while compensating for physiological limitations. In aquatic habitats, some fish follow chemical plumes drifting through reefs at night, interpreting cues from feeding, movement, or reproductive activity to locate prey or mates in conditions where visibility is reduced. These fish continually adjust swimming direction to follow gradients of increasing chemical concentration, navigating complex reef structures, locating organisms hidden among corals, and responding dynamically to currents and temperature-driven dispersion, demonstrating the importance of chemical information in nocturnal aquatic foraging. Nocturnal spiders also exhibit remarkable behavioral flexibility, rebuilding webs nightly in response to changing humidity, insect activity, and wind patterns. By adjusting thread spacing, angles, and anchoring points, spiders optimize silk elasticity and stickiness for maximal prey capture efficiency. Fresh webs mitigate structural damage and environmental wear, while improving hunting success, reflecting a continuous evaluation of environmental cues and an ability to tailor physical structures to nocturnal challenges. Some owls hunt beneath snow cover by interpreting sounds transmitted through layers of ice and snow, discerning the movements of hidden prey such as rodents or small mammals. The snow filters and distorts sound, yet owls use facial structures to funnel acoustic information to their ears, allowing precise localization of prey in 3 dimensions and calculation of depth to ensure accurate capture, conserving energy, and maintaining feeding efficiency during harsh winter nights when visual cues are minimal. Bats navigating cave systems exemplify spatial memory in combination with echolocation. In environments with tight passages, uneven walls, and complex chambers, bats memorize routes to navigate efficiently while using echolocation for real-time obstacle avoidance. This spatial memory enables long-term orientation and optimal movement through intricate environments that echolocation alone cannot fully map, showcasing a sophisticated interplay between cognitive and sensory adaptations. Across these examples, from rodents timing foraging to exploit cool nighttime conditions, to birds detecting subtle air pressure shifts, insects amplifying faint sounds, frogs communicating via fluorescence, mammals adjusting metabolism, reptiles relying on residual heat, fish tracking chemical plumes, spiders rebuilding webs nightly, owls listening through snow, and bats memorizing cave systems. Nocturnal animals display an extraordinary array of behavioral, physiological, and sensory adaptations. These adaptations reveal that life active in darkness relies on a finely tuned integration of multiple modalities, combining energy conservation, risk mitigation, precise environmental sensing, and complex social or ecological coordination. In each case, survival at night is not a matter of mere endurance but a demonstration of evolutionary ingenuity, where animals have evolved strategies that exploit sensory opportunities, environmental consistencies, and behavioral timing to maintain foraging success, avoid predation, communicate effectively, and navigate their habitats with remarkable efficiency. Nighttime becomes a dynamic and challenging environment that rewards specialization, requiring animals to employ chemical, auditory, thermal, visual, and tactile information to solve problems of predation, foraging, and reproduction. The behaviors of these nocturnal species illustrate how life can thrive under constraints that limit daylight activity, revealing ecosystems that operate on rhythms and cues distinct from those governing daytime life. Where subtle environmental signals are amplified, energy is conserved intelligently, and physiological and behavioral adaptations intersect to create complex, responsive strategies. Collectively, these strategies demonstrate the extraordinary versatility of nocturnal species, showing that darkness is not merely a period of inactivity or vulnerability, but a rich domain of opportunity in which evolution has sculpted finely tuned sensory systems, adaptive behaviors, and precise physiological mechanisms that ensure survival, reproduction, and ecological success. With each species leveraging unique combinations of environmental perception, behavioral timing, and energetic management to navigate a world where sight is limited, threats are pervasive, and opportunities emerge in subtle, often imperceptible ways. The behavior becomes especially important when prey species move silently or hide in burrows, as many nocturnal predators and animals rely on non-visual sensory cues to navigate and hunt under the cover of darkness, demonstrating a shift in sensory emphasis according to environmental demands. Certain snakes, for example, depend primarily on chemical cues rather than sight, enabling them to track prey even in total darkness, maintaining precise navigation and foraging efficiency while minimizing exposure to potential threats. This chemical reliance is part of a broader pattern among nocturnal animals, in which auditory, chemical, thermal, and tactile cues often surpass visual information in importance. Bats provide a particularly striking example of auditory-based nocturnal orientation, following the steady sound of rivers at night to locate feeding areas. Flowing water produces consistent acoustic signatures that remain reliable even amid environmental noise caused by wind, rustling vegetation, or other animal activity. In the absence of visual markers, bats use these sounds as directional anchors, allowing them to fly directly to locations where insect prey congregates, often resulting in predictable feeding opportunities. As bats approach these areas, subtle variations in the water's sound indicate bends, open banks, and narrow channels, which they integrate with echolocation to build a layered understanding of their surroundings, conserving energy by avoiding random searching and enabling return to familiar feeding grounds night after night without relying on landmarks. Similarly, certain rodents move across soft soil to mask their footsteps, a crucial behavior in habitats where predators keenly detect ground vibrations. Hard surfaces amplify sound, so these rodents choose paths covered with leaf litter, sand, or loose soil to reduce acoustic signatures. They also adjust stride length and movement speed to minimize noise, using whiskers and tactile feedback to judge terrain softness before committing to a path. This silent approach not only decreases predator encounters but also facilitates stealthy foraging and reduces competition with other nocturnal species, illustrating how minor adjustments in movement and terrain selection become essential survival strategies in ecosystems where sound travels farther than light. Nocturnal birds demonstrate similar adaptive sensitivity by adjusting migration routes based on stable night winds, exploiting nighttime atmospheric conditions that differ from daytime patterns to conserve energy during long journeys. They detect changes in air pressure, direction, and temperature while in flight, continuously adjusting their paths to follow favorable wind corridors that reduce energy expenditure, allowing more efficient migration across continents. By choosing altitudes where winds are predictable and avoiding daytime thermal turbulence, these birds minimize overheating and exposure to visual predators, showing how nocturnal migration relies on constant evaluation and flexible decision-making rather than rigid adherence to predetermined routes. Insects also employ specialized adaptations to remain hidden, synchronizing wing beats with ambient vibrations produced by wind, water, or other moving organisms. By blending their movements with background noise, insects reduce the contrast between their activity and the environment, avoiding detection from predators that rely on non-visual cues. This intricate synchronization requires highly sensitive receptors to monitor vibrations in real time and adjust movement instantly, enabling foraging, communication, and locomotion without revealing their presence. The method demonstrates a refined form of camouflage that relies on timing and environmental synchronization rather than appearance alone, highlighting the sophisticated ways nocturnal species exploit natural rhythms to maintain safety. Amphibians, too, use subtle nocturnal adaptations, shifting skin pigment slightly after dark to match cooler nighttime tones. Predators often detect contrast rather than detail, and by adjusting the distribution of pigments, these amphibians reduce their visibility against rocks, soil, or vegetation. The color shifts are subtle, fine-tuning light reflection rather than producing dramatic changes, allowing the animals to remain effectively camouflaged while foraging, moving, or remaining still. The responsiveness of pigment to environmental cues such as humidity, temperature, and background coloration ensures that camouflage remains effective throughout the night, illustrating how small physiological adjustments can enhance survival in dynamic nocturnal landscapes. Mammals, particularly social species, communicate across long distances at night using low-frequency calls that travel efficiently through air and ground while minimizing absorption or scattering. Cooler, denser night air allows these calls to cover wide areas, facilitating coordination, warning of threats, and locating mates without attracting visually oriented predators. Each call conveys information about identity, urgency, or location, and individuals interpret subtle echoes from nearby surfaces to gauge distance, creating an effective communication network when visibility is minimal and scent trails shift with humidity. This combination of low-frequency signaling and environmental awareness highlights how nocturnal species adapt communication strategies to optimize both safety and social cohesion. Spiders illustrate another form of environmental sensitivity, detecting predators through faint tremors transmitted along the ground. Nocturnal spiders often inhabit areas where approaching predators are silent and vision offers limited protection, so they rely on specialized mechanoreceptors in their legs to interpret minute vibrations caused by footsteps, wing movements, or shifting soil. This vibrational awareness allows them to freeze, retreat into burrows, or reposition before a predator approaches, providing a crucial non-visual warning system in the night and demonstrating how physical cues transmitted through substrates can guide survival strategies. Fish, in aquatic nocturnal environments, release pheromones after sunset to attract mates, timing chemical signals to coincide with environmental conditions that maximize efficiency. Cooling water and slowing currents allow predictable signal dispersal, while darkness reduces predation risk associated with active mating displays. By releasing pheromones at night, fish communicate reproductive readiness and territorial information to conspecifics while minimizing exposure to visual predators, and partners locate each other by following chemical gradients, illustrating how nocturnal chemical communication coordinates reproductive behavior across populations while mitigating risk. Reptiles, similarly, use thermal patterns on the ground for navigation after dark, relying on specialized receptors to detect subtle temperature differences between surfaces. Warm areas indicate safe paths or potential prey, while cooler zones may mark water, shade, or obstacles. By integrating thermal information with scent and tactile input, these reptiles create mental maps of their environment that allow confident movement and successful foraging even in minimal visibility. Heat sensing also helps identify prey whose body warmth persists longer than surrounding surfaces, providing an advantage in habitats with predictable nocturnal temperature gradients. Insects navigating long nocturnal flights rely on starlight as an orientation cue, detecting subtle patterns of celestial light to maintain direction when terrestrial or magnetic cues are unavailable. This reliance on visual cues that are faint yet consistent demonstrates the flexibility of nocturnal navigation across multiple sensory modalities, as animals exploit any reliable environmental signal to move efficiently. Across these examples, from chemical reliance in snakes to river-guided bat navigation, soil-sensitive rodent movement, wind-aware bird migration, vibration-synchronized insects, pigment-adjusting amphibians, low-frequency communication in mammals, tremor-detecting spiders, pheromone-signaling fish, thermally guided reptiles, and starlight-oriented insects. Nocturnal life is defined by the interplay of multiple sensory systems finely tuned to environmental conditions. Each species demonstrates that darkness is not simply a limitation but a domain in which sensory adaptation, behavioral timing, and physiological regulation create opportunities for survival, reproduction, and ecological success. Nighttime environments favor subtlety, efficiency, and responsiveness, rewarding species that can integrate chemical, thermal, auditory, tactile, and limited visual cues to make precise decisions under low-light conditions. The diversity of nocturnal strategies illustrates the remarkable versatility of life active in darkness, showing that energy conservation, predator avoidance, navigation, foraging, and social communication all depend on highly refined, often species-specific adaptations that exploit environmental consistencies and natural rhythms. In these habitats, sound can guide movement, temperature can indicate safety, chemical cues can coordinate reproductive behavior, vibrations can signal threats, and faint celestial or reflective cues can support navigation, allowing species to thrive where daylight strategies would fail. The breadth of adaptations underscores that nocturnal life is neither passive nor precarious. Instead, it represents an evolutionary frontier in which complex sensory integration, precise physiological regulation, and flexible behavior combine to solve challenges imposed by darkness. Each animal's approach, whether it involves masking footsteps, blending into ambient vibrations, altering skin pigmentation, following thermal gradients, releasing pheromones, navigating by starlight, or using rivers as auditory anchors, reveals the intricate balance between environmental perception and survival strategy, emphasizing how evolution has shaped the ability of species to exploit niches that are inaccessible or inefficient for diurnal competitors. In essence, nocturnal life exemplifies an ongoing dialogue between organism and environment, where the constraints of darkness are transformed into a landscape rich with opportunity, and survival depends on mastery of subtle signals, precise timing, and coordinated activity across multiple sensory and behavioral channels, creating ecosystems in which the night is not a time of retreat but a period of intricate, highly optimized ecological performance.